You know those beautiful rainbow-like patterns you see in a soap bubble or maybe in an oil slick on a wet road? Well, what if I told you a similar, even more incredible phenomenon can be created with just a simple lens and a pane of glass? Today, we're going to pull back the curtain on the secret of Newton's rings, one of the most stunning displays in all of physics.
It's a great question, right? I mean, on the surface, you might think, not much. They're just simple, transparent objects. But when you put them together in a very specific way, they become a window into the very nature of light itself. It's pretty extraordinary. Let's check it out.
And there it is. Look at that. These mesmerizing, almost hypnotic circles of light and dark. These are Newton's rings, and they're so much more than just a pretty pattern. They're actually a visual map of how light waves interact with each other, a secret code hidden in plain sight.
So, how are we going to crack this code? Well, first, we'll take a closer look at these mysterious rings. Then, we'll see the surprisingly simple setup that creates them. After that, we'll dive into the physics, use a little math to decode the pattern, and finally, see how this all has some pretty powerful real-world applications. All right, let's start at the very beginning. What exactly are we looking at here? How do these rings just appear?
You know, the best part about this whole thing is how simple it is. Seriously, all you need is a plano convex lens. That's just a lens that's flat on one side and curved on the other, and you place it on a flat piece of glass. Shine a light from above, and boom! Just like magic, these incredible concentric rings show up.
So what's really going on in this simple little setup? What's the secret ingredient? Let's zoom in and take a closer look.
So as you can see, the curved lens sitting on the flat plate creates this tiny, wedge-shaped gap of air between them. It's practically non-existent right at the center where they touch, and it gets gradually wider as you move out to the edges. Now, this tiny, almost invisible film of air, that is where all the action happens. Okay, let's follow a single beam of light on its journey. As it comes down, some of it, we'll call it ray 1, bounces right off the bottom surface of the curved lens. But the rest of the light, ray 2, keeps going. It travels through that tiny air gap, bounces off the flat glass plate below, and comes back up. Now, when these two rays, ray 1 and ray 2, meet again, they've traveled slightly different distances, and that little difference is about to cause something amazing. And now we've reached the heart of it all. The reason these rings even exist is because of a fundamental principle of wave physics called interference. It's what happens when light waves collide.
So what exactly is interference? It's really just what happens when two waves run into each other. They can add up to create a bigger, more powerful wave. They can cancel each other out completely. Poof, nothing. Or they can form a new wave somewhere in between.
This idea of a path difference is absolutely key. Think about it. Because ray 2 had to make that extra trip down through the air gap and back up, it's traveled a little farther than ray 1. That tiny delay means the two waves are no longer in sync. They're not marching to the same beat anymore.
And that mismatch is the secret to everything. When the waves are perfectly in sync, when the peak of one wave lines up with the peak of the other, they boost each other up, creating a brighter light. That's constructive interference, and that's where you see the bright rings. But when they're perfectly out of sync, when a peak meets a valley, they completely cancel each other out. That's destructive interference, and it's what creates those perfectly dark rings. Okay, so we've got this incredible pattern, and we know the physics behind it. But can we do more than just admire it? Can we measure it? Predict it? Absolutely. With just a little bit of geometry and math, we can decode this pattern and turn it into a seriously powerful tool. Let's just break down the geometry for a second. There are two really important measurements here. The first is R, the radius of curvature of the lens. That's basically just a number that tells you how curved the lens is. The second is R, which is the radius of any specific ring you want to measure, from the center out to the edge of the ring. So here's the big insight, and it comes from some basic properties of a circle. Turns out that the square of a ring's radius is directly connected to how thick the air film is right at that exact spot. It's a really simple, elegant relationship that connects the physical setup to the pattern we can actually see and measure. And here is where it all comes together. When we combine the physics of interference with the geometry of the lens, we get this incredibly powerful formula. With this, we can actually calculate the wavelength of light. That's what the Greek letter lambda stands for, just by measuring the diameter of a couple of the rings. I mean, how amazing is that? We're measuring a fundamental property of light with such a simple setup.
So this is a really cool lab experiment, but what's the point? What can we actually do with this knowledge?
Well, as it turns out, this simple phenomenon has a whole range of super practical applications out there in the real world.
Let's just run through a few of them. We've already talked about measuring the wavelength of light, but you can also use it in reverse to find the exact curvature of a lens. In manufacturing, it's used to make sure optical surfaces are perfectly, absolutely flat. It can be used to find properties of liquids, measures super thin films, and even helps in making complex lenses for eyeglasses. It's a real workhorse.
But of all those applications, the most profound one, the one that's just a game changer, is the one we've been focused on, getting a precise measurement of light's wavelength. With this incredibly simple experiment, we can directly measure one of the most fundamental properties of the universe.
But what if we mix things up a little? What happens if we replace that air gap with a clear liquid, like water or oil? Well, light travels at a different speed through a liquid, and that changes the path difference for our two rays. And you know what that does? It actually makes the rings shrink. And by measuring exactly how much they shrink, we can calculate the liquid's refractive index, another one of its core properties.
Just as the source material puts it so simply and perfectly, the diameter of the rings reduces in liquid. That direct, observable change lets us measure an invisible property of a material. That's the power of this experiment in a nutshell.
And that kind of brings us to a final big question, doesn't it? With just a lens and a piece of glass, we managed to unlock the secrets of light's wavelengths and a liquid's refractive index. It really makes you wonder, what other profound secrets about how our universe works are just hiding out there, in plain sight, waiting for us to find the right way to look at them? Thanks for joining me.